newest person to the channel. It's been 8 minutes and nobody showed up, so we're going to do this. Okay, for the CP class, we're looking at vectors and average velocity this week. We'll cover some of this in class, but just kind of a general overview so you have it if you ever get confused. We're going to cover it in here. Starting off, though, with the realm of vectors. What's your vector, Victor? Haven't seen airplane. That's a joke you didn't get, but do your best to keep up. Basically, we have from, kindergarten, the number line. 0, 1, 2, 3, 4, da 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 da, on and on. And then sometime in, I don't know, what was it, like 5th grade, you had negative numbers, okay? These are your number lines. And traditionally, whenever we count so far on our number line, like we've gone 1, 2, 3, we would get some number there, okay? And if you went in the other direction, big idea. You went -3, way to go. This number, this just size of something, this is what is referred to as a magnitude. Pop, pop, magnitude. That's a community reference if you didn't get that either. So, oh man, I'm old. Okay, so the number of something is just the magnitude. Now the issue is that 3 could be this way or this way, because technically the magnitude of going in the negative direction is just, it's still 3. You've gone a total of 3. It doesn't matter if you went to the right, it doesn't matter if you went to the left. The magnitude of something is just how many did you go. So in that regard, the magnitude of both of these here is indeed 3, despite the fact that we went positive or negative. Now with a vector, everything changes. With a vector, oh, I shouldn't say everything changes. But a vector does not just have magnitude. Technically speaking, if you only have a magnitude, what you really have isn't a vector. What you have is called a scalar, okay? And it is only a magnitude. So it's only the size of something. Common scalars that exist are things like mass, distances, time can technically be considered a scalar. These are just common scalars that we are going to use throughout the year. If you're an AP2 kid sneaking in here, we'll also see that work is a scalar, which means that energy needs to be a scalar, and then that gives us voltages, which are technically scalars, as these are potentials. These values, while they could have sign, really they're a magnitude, they're scalar quantities. We're not overly concerned with the positive or negative, although I will put a asterisk next to a few of these because things get weird. We'll talk about those as we go on in the year. A vector, on the other hand, it not only has a magnitude, but it also has, and this is the big key for a vector, a direction. Okay, it needs this direction. It has both of these though, magnitude and a direction. So if we take a look at what we have here, if this is our 0 point here, we go 1, 2, 3 to the right, we've gone +3. We go 1, 2, that's I guess 3 to the left, we've gone -3. Now notice how I've drawn my vector with this arrow here, because when you draw a vector, you must draw it as a line of some length, so that length is representative of the magnitude, but the direction you go is based off of the arrow. And note, if this line is the magnitude, this is an important little feature. Everybody messes this up. I mentioned this in class. Do not make your arrow like this, because you've actually just given extra length to the vector, and that's just weird. The proper way in which to make your vector arrow and direction is from the top of your line to go backwards from it. So see, now you have the proper length and you know the direction it is going. It has a magnitude, some length, some size to it, and it has a direction, okay? So keep that in mind as we're playing with vectors. We will do a whole lot more stuff with them, but in general, they have a magnitude and a direction. Because of this, and you'll kind of notice it in this vector here, the orange one, it does not need to sit on the x-axis as we kind of see above it in the example, the +3, -3. It doesn't need to sit on the y-axis either. You know, if I draw an x and y-axis in here, this thing is just kind of going into the first quadrant. So there's the y-axis, there's the x-axis. This isn't on either of those. We will see later on in the year how we can get this back into the proper x and y axes, and how we can also use a few different ways of measuring this location. We can use standard Cartesian coordinates, which are just x comma y. We can use polar coordinates, which are the length of the vector, the magnitude, and its position going around a circle. And we'll be using unit vector notation, which is some amount in the I hat direction plus some amount in the j hat direction. And I'll just tag over here that, whoa, that is big, that the I hat direction represents the x-axis, the j hat direction represents the y, and if we get to it, the k hat direction represents the z if you're ever in three-dimensional space. Okay, we'll talk about all this stuff. We'll talk about how we can find these angles going from the x-axis going around, and how we can eventually break all of this stuff up with SOHCAHTOA when we get there. Okay, we're just not there yet, so we're gonna skip by that. What I'd like to talk about though now that kind of relates back up into your lab is this idea of an average velocity. When we think about average velocities, we need to be careful because technically the equation v equals delta x over t, this is technically speaking an average velocity, okay? We only really use this equation when the acceleration equals 0. And the reason why we do that, and which we saw in the lab, is because when this acceleration is 0, the initial velocity and the final velocity are the same. So the average is the initial or the final. That doesn't matter. Every point in this is the same if your acceleration is 0. Okay? So we need to be careful about that for this average velocity. That's technically what this here is telling us. Although we'll never see it written like that. It's never written like that. But we do need to be careful about that there. That's super, super important. If our acceleration is not 0, we will use a different equation. Guaranteed, every time, 100%. Don't make that mistake. So just be aware. The only other thing we really can think about whenever we're looking for a time average velocity, and we'll talk about this in class, is if we're looking for a time average velocity, then we need to basically take all of the distances and look at how long the times have happened at each of those because at each region there is a corresponding amount of time it has gone through. So in this case here, we are pretending that it is going at the same speed for the same amount of time. But what happens if you have a scenario where your horse is kind of like, well, I guess a horse is an easy thing. You have 3 different velocities. Like you've gone 25 miles per hour, and then for, I don't know, for 3 minutes, and then you go 50 miles per hour for 1 minute. Okay? That right there, if we are averaging velocities, is going to be a little weird, because essentially what we have here is we have gone 25 miles per hour plus 25 miles per hour plus 25 miles per hour plus 50 miles per hour. Okay, so we've got 3 minutes of boom, 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 and 1 minute of this. So there's 3 times as many 25s as the 50 here. But then, just like any other average, you divide it by that full amount. So just by looking at this here, you can't really say that between 25 and 50, my average is, 75 divided by 2, because it's not anymore. It's actually going to be 25, 50, 75, 125 divided by 4 miles per hour. This is something we got to be careful of right here, okay? In general, what we're doing is we are taking each velocity per amount of time and adding it up, and then dividing by our total amount of time here, okay? So the way this is kind of going to look if we ever run it is our average velocity, if we have distinct velocities we are traveling at, it will be essentially different velocities that we have divided by the full amount of time, and we're looking at each of those velocities in the time segment, okay? I think we'll show this next week, because I think that's something that I want to show in class right now, because we're going to look at this tomorrow on the 14th, and this is something that if you have questions in class, please ask it. Maybe I'll post something up over the weekend, but it goes right here, okay? So please be aware of that as you're looking through here for those average velocities. We'll definitely have some homework problems on it. We'll definitely see it on the test. It's a no-brainer, but please be aware that it's not just saying 25 plus 50 divide by 2. It's 25, 25, 25, because we have 3 of them, and one of the 50s divide by 4, because we have a total amount there, okay? So I'm going to bounce off now.